In this video, it's going to be a little different than the previous videos. We're going to sort of casually talk about arrays. So, the most popular way of working with data that comes in, say, like vector and matrix form, is to use a Numpy array. Now, Numpy arrays are a little better than pure Python. I think they're built on top of faster coding languages such as C. But these arrays let us do math in a much more intelligent way. For example, let's look at a list. If we have a list 0, 1, 2, 3, and we want to multiply those values by 5, we can try run this, but what we did is we duplicated the list 5 times. Now, if I'm using NumPy, I'm going to import the NumPy library as MP. So I'm saving an entire library of code onto this variable name, so I can call the code using this variable. We can convert this to an array, np.array, and let's take this list and pass it in there. And it can intelligently know that we're not just trying to get the list multiplied 5 times, we're trying to multiply each value in the list by 5. So now we get 0, 5, 10, 15 as our output. Okay, so what's really the use of this thing? Couldn't I iterate through, couldn't I find a solution where I do like, oh, maybe item times 5 for item in this list. And I will in fact get the right result, 0, 5, 10, 15, just like NumPy. Well, first off, like I said, it's slower, but also NumPy has way more functionality than these simple things. So if I were to add 5, it'd be simply plus 5. Let's go ahead and run that. So we get 0 plus 5 is 5, 1 plus 5 is 6, etc. And we can do all kinds of simple stuff like that. But importantly, NumPy has a lot of really nice things built in. So let's just talk about stuff that you can do with NumPy, because you'll encounter these arrays a lot when you're doing scientific computing tasks. So first, one thing we can do that's very convenient is we can generate linearly spaced data. So let's say lin-spaced array is equal to np.linspace for linearly spaced, and over here we get a start point, a stop point, and the number of datum we want between those 2 points. And so we can do that. We can do 0 as our starting point, 1 as our ending point, and let's say we want 5 data points in there. So we can run this, and we get lin-spaced array as 0, 0.25, 0.5, 0.75, and 1. Notice how this includes both the start point and the end point. Now, let's say you want not a number of items between 2 points, but you want to generate points that are spaced by a specific value. So we can also do a ranged array. And this would be np.arange, and we can give it a start. And I'm going to explicitly code this in. We could have done this with the linspace as well. We'll give it a stop, and these are called keyword arguments because we have a keyword plus the argument to the function. And let's say we want a step. So if our step is equal to 10, we're going to generate things spaced out. In fact, let's just look at it. So we get a 0. Why do we get a 0? Because I started at 0, I tried to take a step of size 10, and there was no step available that was less than this value here, 1. So if we were to stop at, let's say, 20, try to predict what will happen. Well, it's either going to do 0, 10, 20, or it's actually just going to grab 0 and 10. This stopping point is like a parenthesis bracket on a number line. So you can think of it like this, where we're going up to 20 but not including 20. So since 10 by 2 is exactly 20, we couldn't include that value. And that's just how these arranged arrays work. Now there's other things we can do with NumPy. One thing that's very convenient, I'll call this a 2D array, so we can work with matrices here, is np.random. This is the module that allows us to do all kinds of generation of random numbers. And we can do random integers, we can do random from a normal distribution, etc. Let's do random integers, and we'll give it a low integer, so let's start at 0. We can go up to 100, and we can tell it the size. So I want this 2D array to be a 2 by 4 array. So let's go ahead and hit run, and it's going to generate random integers between 0 and 99, since it doesn't go up to 100 just like it does, just like up here. We can double check that. If we hover over it, it should tell us. It's a little bit messy. Let's click in here. So it should tell us whether or not this endpoint is included. So high, provided one above the largest signed integer to be drawn from the distribution. So if provided, it's one above the integers that are drawn from the distribution. Okay, so yeah, 0 to 99 with size 2 to 4. So let's go ahead and look at this. So we've built this array 2D. It's an array of int32 values of size 2, 4. And if we open it up, what we get is 2. Notice that's the rows. We have 2 rows by 4 columns. So this is our little 2 by 4 matrix. Now we could do this for up to any size. If we want our matrix to be not just 2-dimensional but 3-dimensional, this is valid. We can go 4-dimensional and 5-dimensional, whatever you want. Now you're not going to be displaying that because Spider can't display more than 3 dimensions. So if we go back down to here, let's look at how to display 3 dimensions. So we have a slice with our 4 by 2. So we have our 4 by 2, and there's 2 different versions. So if I go down to this index, we have the first version and then the second version of our 4 by 2. So that's what we're looking at here. Let me just click off there so you can see. And these are all randomly generated numbers, and it's a quick and easy way to fill an array. Awesome. So what else can we do? Well, we can do normal slicing and normal indexing and normal concatenating. To concatenate, instead of just adding, like with 2 strings, you do this. What we do is we do np.concatenate. And then this gives us sort of an example. Everything we want concatenated goes in a tuple, which is the first argument. And then you tell it the axis. Axis equals 0 means to concatenate downward. So if I had this, let's make this a 2 by 4 again. If I had this 2 by 4, and I concatenated another one that was identical along axis 0, it would then be a 4 by 4 because we concatenated down through here. If I concatenate along axis 1, it becomes a 2 by 8. So that's what the axis argument was here. So in our case, we have this array 2D. Let's make a second one just so we can see. So v2. So this is what the first one looks like. Let's run these two. The first one's here. The second one's here. And if we concatenate along, I'm going to explicitly say this, even though by default axis is 0, I'm going to explicitly say axis 0. We get that little guy, and let's go ahead and open him up in the variable explorer. Oops, there we go. So we get that 4 by 4. So the 2 by 2, or a 2 by 4 concatenated with a 2 by 4 along axis 0 is a 4 by 4. If we change this to axis 1, we'll rerun that, and now we get that 2 by 8 I was talking about. Perfect. So that's concatenation. And you can do all of that normal arithmetic. So when I showed you this up here, np.array, and here, let's go ahead and delete that stuff, and I multiplied it by 5, this is what's called broadcasting. So it broadcasts this operation onto each item in my array. And you can do that with, I think, all operations, all your standard arithmetic operations. There you go. What else can we do with this? Well, there's some really nice things. If you have a list of data, you can get descriptive statistics. So let's take this array 2D, this 2 by 4. Let's go ahead and open them up and look at them. We could, if we wanted, sum up all of these values. And how we do that is we do array2d dot sum. I haven't given it any axes to sum over, so it's going to sum the entire thing, returning 388. Now if we want the summation across axis 1, we can do axis equals 1. And we'll run that, and we see we get a 195 and a 193. If we do it along axis 0, we get a 110, 143, 88, and 47. So we can also do a min, and that's the minimum of all things along axis 0. We could do a max, and that's the maximum values, 87, 80, 46, and 44. We could do something like the standard deviation. We could do the variance. We could do the mean, or we can do the cumulative sum. So let's look at that one, the cumulative sum. Now along axis 0, what we're going to get is this little guy here. First it's 87, 63, 42, 3, 110, 143, 88, 47. So this adds to 110, this adds to 143, this is 88, and this is 47. So that's the cumulative sum. Now besides that, a quick thing we can do when we don't know what an array looks like is we can ask for the shape of the array. So working with array2d, we can do .shape, and this returns the dimensions of the array. So in our case, we had 2 rows, 4 columns. It shows us that there are in fact 2 rows, 4 columns. If we do array2d v2 here on line 10, we can add a third dimension, and if we take the shape of this, it'll show us that third dimension. Perfect. Okay. So moving away from things you can do to arrays, or like methods associated with arrays. So once I have an array, I can do dot something. NumPy has a lot of built-in stuff that's often really useful to access. np.square root will take the square root of either a value, so I could put 9 in here and it'll return 3, or an array. So array2d can go in here, and it'll return the square root of everything in that array. Similarly, we can do the exponential, we can do the log. I'm going to skip writing the np dot, but this is going to be how we do it. So the log, we can do the sine, we can do tan h, we can do the tangent, we can do the dot product, and this would be an array, let's say 2D, and let's dot it with itself. So we'll take array 2D, and notice I'm going to need to transpose it. This is the transpose for that dot product. And let's just run that just to make sure. Okay, np dot, just to make sure it works how I expect. Perfect, so the dot product of that. Boom and boom. Other things we can do, we can get the correlation coefficient. So this will return the correlation coefficient between things in the array. So if we take array2d, let's grab this np dot, we can see how correlated each item is to themselves. And let's go ahead and save this in a variable. So we can open it up with that nice pretty variable explorer we have here. We can see they're perfect. These 2 items are perfectly correlated with themselves, and these 2 are not. And notice it's 2-dimensional. That's because we have a 2 by 4 array. If we take the transpose of this, we can see what happens. Well, var opens up as a 4 by 4. Okay. The next thing we can look at, we have that correlation coefficient. We can also take a median, or I believe that's about all of them, but there's lots of other documentation where you can probably find there's lots of extra stuff we can do. We can even, I think, get like the full description of the statistics. But look that one up in Google and see what you see. And then finally, something that's often overlooked but extremely, extremely useful is we can use logic with these NumPy arrays. So we have array2d, that's our our favorite one right now. Let's go ahead and open him up so we can inspect him as we're doing this. Let us try to find all values greater than or equal to 80. So an easy thing we can do here is for array2d, we can ask it what values are greater than or equal to 80. And if we run this, it's going to return trues where it's true and falses everywhere else. So I'm just going to go ahead and call this logic. And I'm going to run it. Let's just go ahead and open that variable. Open that variable and see how it compares. So we have our true and all of our falses. So here, what NumPy arrays can do is they can perform logic on themselves and give you back this new array where you can re-index. So let's say I want to change all of the values greater than 80 to be equal to 99. I can say array2d in the locations that were true, make that equal to 99. And so let's go ahead and save this to a variable. I'll call this var2. And I've run it. Let's see. There we go. It's ran. Let's open it up. Oh, I have two 99s here. So what I messed up with is this is actually updating array2 in place. So it's grabbing this array, this object, and it's saying where things are true, change your actual values. So it's not returning something new, it's changing this object itself. So let's go back here and let's look. This is the old version of array2d. And here we have the new version where things were greater than 80, where we had those true values over here, we can now change their value. So that's just a small taste of what NumPy arrays can do. But you'll find that they're almost always the right answer, though they could be tricky to use them. And it might be easier to just do for loops or while loops and brute force in a slightly slower manner the same solution. So good luck, and I hope this video helps.